Welcome to the another video on VLSI design. In this video, we are going to discuss current voltage characteristics of transistor. Specifically, we are going to focus on the IV characteristics of MOSFET device. Firstly, let us consider NMOS transistor. NMOS stands for N-channel metal oxide semiconductor field effect transistor. So let us consider NMOS transistor. The characteristics of NMOS transistor falls in the first quadrant because of voltages that we apply, and the currents are going to be positive. So therefore IV characteristics falls in the first quadrant. So according to the first order model, so there are three currents which we need to discuss here. The number one is the drain source current in the cutoff region. So IDS is nothing but the drain to source current that is flowing, which will be equal to 0 for gate to source voltage less than the threshold voltage. This condition is called as a cutoff region. So to operate transistor, NMOS transistor in the cutoff region, the gate to source voltage needs to be less than the threshold voltage. Typically, threshold voltage VTP or VTN here is going to be 0.3 volts. That is considered throughout this textbook. So we will retain the same threshold voltage even in this course as well. So if when the gate to source voltage is less than 0.3, definitely there will be no current flow through the MOSFET between the drain and source. So therefore IDS is going to be 0. The next is going to be the linear region, so which we indicate here with capital L. So how to operate MOSFET in the linear region? To operate MOSFET in the linear region, VGS must be greater than the threshold voltage. The gate to source voltage that we apply should be greater than the threshold voltage of a MOSFET, which is 0.3 volts. And second condition is, there are two conditions of course for to operate MOSFET in the linear region. The first condition is gate to source voltage must be greater than 0.3 volt. The second condition is the drain to source voltage must be less than the effective gate voltage, or VGS minus VT. VGS minus VT sometimes we call as VGT as well. So this effective, the difference is called as effective gate voltage. So the VDS must be less than this effective gate voltage. So these are the two conditions that we need to satisfied to operate N-channel MOSFET in the linear region. The current that is flowing in the linear region is given by this mathematical expression. The current, the drain to source current, equals beta n. So beta n is nothing but it is mu into, right here, beta n is nothing but mu times COX into W by L. That is going to be the beta. Okay, I will write separately so that people understand here. So beta is nothing but beta is made up of two parameters. Mu is mobility and COX is oxide capacitance, and that is multiplied with I'll put a bracket here, and that is multiplied with width to length ratio. Okay, so this is the expression for the beta. So yes, straight away we take a beta value. So therefore IDS equals beta n, the subscript n indicates it's for the NMOS transistor. That's multiplied with VGS minus VT times VDS. So we have a bracket over here. So that's multiplied with VDS minus VDS square divided by 2. So this is the current, drain to source current, that is flowing in the linear region, and for these conditions that we already set. The next current is going to be the saturation current. Now question is, how do we operate MOSFET in the saturation region? To operate MOSFET in the saturation region, similar to linear region, we need to have two conditions to be satisfied. Number one is gate to source voltage must be greater than threshold voltage VT, and which is 0.3 volts. Number two is, in this linear region we have taken drain to source voltage less than the effective gate voltage, but here to operate MOSFET in the saturation region, the drain to source voltage must be greater than gate to source voltage minus VT, which is effective gate voltage. If VDS is greater than this and VGS is greater than the threshold voltage, then definitely this is the setup for MOSFET to operate in the saturation region. Saturation region we indicate with the uppercase S. The current that flows in the saturation region is given by IDS equals beta n by 2. Here we have a 2 divided by 2 that we need to understand here. So VGS minus VT whole square. In the previous video, we have shown how to derive all these equations, but now we are considering the final results to draw the characteristics of NMOS and PMOS. So IDS equals beta n by 2 into VGS minus VT whole square. The square is the okay. So these are the three regions of operations, namely cutoff region, linear region, and the saturation region. And we have shown the conditions to operate in each of these regions, followed by the current that flows in all the regions. Okay. So now let us do a little bit of analysis before we go to the drawing of characteristics. As we already said, uppercase C stands for cutoff region, L stands for linear region, and S stands for saturation region. And let us see, as per this equation, let us see the dependent of drain to source current on voltage. Specifically in linear region, if we observe this linear region current equation, the drain to source current IDS is a function of gate to source voltage and drain to source voltage. As we can see, the IDS equation is now dependent on VGS and as well as VDS. We have at two places we have drain to source voltage, so therefore we can write it here as IDS is a function of VGS and VDS, specifically in the linear region. What do you mean by this? So the meaning of this is, as VGS is varied, increased or decreased, and in the drain to source current can be altered. In a similar way, the drain to source voltage, if it is changed, if it is increased or decreased, the drain to source current can be varied. That means the drain to source current depends on both the voltages, that is gate to source voltage and drain to source voltage. Unlike in linear region, the saturation region is little different. In the saturation region, the drain to source current completely depends on the gate to source voltage, and it becomes independent of drain to source voltage. It is not a function of drain to source voltage. Any variations in the drain to source voltage will not affect the drain to source current. However, any variations in the gate to source voltage that generally affects drain to source current. So these are the things which we need to consider, which we can come out as a conclusion of these equations that we have shown. Okay, and when we go through the equations 1, 2, and 3, that is basically the cutoff region current equation, linear region current equation, and saturation region current equation. All these three equations overestimates the current at high voltage, because these are all the first order model equations. Therefore, the three current equations overestimates especially the currents specifically at high voltages. And also the second thing what we need to consider here is the three equations that we have shown here that doesn't account for mobility degradation. These are the secondary effects which we will discuss in the upcoming videos. So this doesn't take care of degradation of the charge carriers due to the mobility degradation effect, and also it doesn't take care of the velocity saturation effect, which is mainly caused due to the high electric fields. These two are not considered in the first order model. Therefore, based on these two reasons, we can say that the three currents that we have discussed overestimates the current specifically at high voltages. Okay, that's about the NMOS transistor background. And now let us move to the characteristics before we go to the PMOS transistor. Let me show the characteristics of NMOS transistor. So this is how we plot the characteristics for NMOS transistor. As we already mentioned, the characteristics, IV characteristics of NMOS transistor falls in the first quadrant because of the drain to source voltage, the applied drain to source voltage, and the drain to source current both are going to be positive. So therefore, we can draw the VDS versus IDS graph in the first quadrant for constant gate source voltage. So gate source voltage must be kept constant, and for every gate source voltage, the VDS drain to source voltage must be varied in steps, and the current that we obtain that can be plotted along the y-axis. Here, for simplicity, we have taken a couple of gate source voltage, namely the 0.4, 0.6, 0.8 and 1.0. These are the various gate to source voltage that we have preferred here. And drain to source voltage is plotted along the x-axis. As we can see that x-axis is drain to source voltage that is incremented at the rate of 0.2 volts. We have 0.2, 0.4, 0.6 up to 1.2 volts. We have taken the scale along the x-axis. So VDS is going to be in volts, and y-axis is nothing but the drain to source current. Typically the drain to source current is going to be in microamperes, especially for the sub-threshold, the MOSFET, the drain to source current is going to be in microampere. The drain to source current is 50 microampere, 100 and 150 microampere. That's going to be the scale that we have taken along the y-axis. And gate to source voltage is again varied in terms of 0.4, 0.6 and 0.8. And the threshold voltage preferred here is going to be 0.3 volts. This is the assumed threshold voltage for sub-threshold the MOSFET. So 0.3 volts, and let us plot the characteristics for various gate to source voltage. Let us select the gate to source voltage as 0.4 volts, and we'll see that different regions of operations. So firstly, as we have already said that when the gate to source voltage is less than threshold, when the gate to source voltage is less than the threshold 0.3, the device remains in the cutoff region. Therefore, the characteristics falls in the x-axis, just like this. So the characteristics falls on the x-axis. So therefore, the characteristics in this region can be called as cutoff region. So cutoff region. Okay. As we keep increasing gate to source voltage above threshold means threshold is taken as 0.3 volts. Say for example, VGS is taken as 0.4 volts. We can see that how exactly current varies. In the beginning, when the drain to source voltage is very small, we can see here there is a linear region comes into a play. So we have a small linear region, and further what happens we can see here when drain to source voltage is increased. So the current becomes almost like a saturation. So this is a saturation region. So now we will estimate here at what point the saturation region commences. So as we know that this is the equation, VDS equals VGS minus VT. This equation tells us, it gives you the mathematical boundary between the linear region and the saturation region. So we already know here VGS as 0.4 volts. Threshold voltage of the MOSFET is also known, which is 0.3 volts. So therefore, the boundary for this particular curve is 0.4 minus 0.3, that gives you 0.1. So somewhere here we have 0.1. So that is the point 0.1 volts. I'll put an into mark here. Till here it is going to be linear region. After 0.1 volt, when VDS exceeds 0.1, the saturation commences. It is better to show this saturation in different color so that we can understand. So saturation is this. So saturation commences at 0.1 volts and above. Let us go for another curve and try to understand the commencement of saturation and end of the linear region. Let's say we have preferred 0.6 volts. So let us substitute here VGS as 0.6, VT is 0.3. Saturation commences at 0.3 itself. So 0.3 is somewhere here. This is a rough scale I have taken here. So 0.3 is here. So therefore you can see here from 0.3 onwards the saturation has been commenced. Then where exactly linear ends? The linear region ends here. Okay. So this is the linear region. Okay. In this way, we can show both the linear region and followed by the saturation region. So VGS is equal to 0.8 volts. So 0.5 is going to be the end of linear region. Let me show that in red color. So 0 till 0.5, it's going to be the linear region, and beyond that, we will have saturation region. So this point is 0. Right in red color so that we can see. So 0.5 volts, sorry, and here we have 0.3 volts, and here we have 0.1 volt. So these are the voltages at which linear region ends and saturation region commences. Similarly, let us go for the last one, which is VGS equals 1 volt, and when we subtract threshold from this 1 volt, we get 0.7 volts. So therefore, at 0.7, let us put it, this is 0.7 volts where the saturation commences. So till that we have a linear region. So we have a linear region, and we have followed by that we have saturation region that commences at 0.7. Okay, when we draw the all these points, we get a locus here, as we can see here. To just like show you the locus here, which is the separation between the linear region and the cutoff region. Towards left side we have a linear region, and towards right side we have a saturation region, and on the x-axis we have a cutoff region here. Now in all the digital systems, the transistors, especially NMOS transistor, switches between the linear region and the cutoff region. These are the NMOS switches. Okay. When it wants to remain in the off state, it goes to the cutoff. When the transistor wants to remain in on state, it comes to the linear region. Here the transistor can be used as on switch. Okay, this is NMOS remains as on switch, whereas here in the cutoff region, NMOS remains as off switch. Okay, so here NMOS remains as off switch. We have a boundary here where we can operate a transistor in the for the analog applications, where we can use transistor as amplifier. In general, the analog applications, all analog applications falls in the saturation region. All analog applications. Example is amplifiers, phase locked loops, and we have the timers, multivibrators. All these applications we can develop in the analog application point of view. Okay, so this is how we can operate transistor, and this characteristics is called as drain characteristics, because we have drawn the characteristics of drain to source voltage versus drain to source current for fixed gate to source voltage, and we have taken around four the graphs here, four characteristics to show how exactly the drain current varies with reference to the drain to source voltage. Okay, so this is for the NMOS enhancement transistor. So we'll show the similar way how exactly the characteristics of PMOS varies with reference to drain source voltage. Now let us study the PMOS transistor the properties before we go to draw the characteristics. Alright, so PMOS transistor. So PMOS transistor behaves in the similar way as the NMOS transistor, but with the there is a signs of all voltages and currents are going to be reversed. We have all negative voltages and currents. So we have a negative voltage and a negative current for PMOS transistors. Therefore, the characteristics, drain to source characteristics for the PMOS transistor falls in the third quadrant. And also one more observation with reference to the PMOS transistor is, if you look at the mobility, mu n, electron mobility versus the hole mobility, according to the theoretical estimation, it is 2 to 3 times. That means the electron mobility is 2 to 3 times the hole's mobility. Another way, holes move at lesser speed compared to the electrons. And the threshold voltage that we choose here is going to be the negative voltage minus 0.3. Just like in NMOS we have chosen plus 0.3, but here we have assumed threshold voltage as minus 0.3 volts. Now let us try to write the current equations in different regions. So drain to source current is going to be 0 for gate to source voltage greater than the threshold voltage. So here we have this device, and P channel device operates for a negative threshold voltage, but if we increase the gate to source voltage above the threshold voltage, the device goes to cutoff region. So this is the current in the cutoff region. Drain to source current remains as 0 in the cutoff region, similar to NMOS device. Let us see the current in the linear and the saturation region. The drain to source current in linear region is minus beta P. We already explained what is beta. Beta consists of process parameters and a geometry of a transistor, so which is W by L. So it is negative here. That is an observation which we need to do. And these terms remain same as the NMOS transistor, which is VGS minus VTP into VDS minus VDS square divided by 2. So this is the drain to source current that flows in the linear region, for which the VDS must be greater than VGS minus VT. That is the condition required to operate PMOS transistor in the linear region, and VGS must be, that is not shown here, that must be less than VTP. If we are able to satisfy these two conditions, then P channel MOSFET will be operated in the linear region, and the current that flows in the linear region is given by this mathematical expression here. Next, let us see the current that flows in the saturation region. The condition required to establish MOSFET in the saturation region is VDS should be less than VGS minus VT. That is the second condition, and of course the first condition remains same as usual here. VGS must be less than threshold voltage. That means if we apply gate to source voltage more negative than minus 0.3, because minus 0.3 is going to be the threshold voltage, then the MOSFET enters into the saturation region. So these are the two conditions that we need to meet to operate the PMOS transistor in the saturation region. And the current that flows in the saturation region is IDS, drain to source current, equals minus beta P by 2 into VGS minus VT whole square. The expression remains the same, which are similar to that of NMOS transistor. So therefore, these are the various current equations for cutoff, linear and saturation region. Now let us draw the characteristics for the PMOS transistor. So here we have NMOS transistor. One thing which I forgot to discuss with you is the current that is governed by this equation. These curves, all these curves are given by the equation we have labeled as 1, 2 and 3. So therefore I would like to mention, so all these red colors what I have shown here, those are the curves that obey equation 2, because this is the current that is, these are the various curves in the linear region. Therefore equation 2 is valid for all these curves for different values of VGS, of course. Whereas all these green curves that I've shown here, for this equation 3 is valid. So this is according to the equation 3. Whereas in the cutoff region, equation 1 is valid. So here we have cutoff region. This works according to equation 1. Okay, so that's the thing which I forgot to mention in the NMOS characteristics. Now let us move to the PMOS characteristics. As we can see here, for the PMOS transistor, drain to source voltage is negative, and even the drain to source current is also going to be negative. So both are negative, the voltage and the current. Therefore the characteristics falls in the third quadrant of the graph. And you can see the scale once again. The drain to source voltage is varied in terms of 0.2, minus 0.2, minus 0.4, minus 0.6, 0.8, and namely roughly it's minus 1.0. The threshold voltage chosen here is minus 0.3, which we call as VTP equals minus 0.3. and the drain to source current is taken as minus 50 microampere, minus 100 and minus 150 microampere. Now when you plot a graph of VDS versus minus VDS versus minus IDS for a constant negative gate source voltage, the characteristics is called as drain characteristics. Okay, let us now plot the characteristics, and let us choose now gate to source voltage as minus 0.4, and similar to the NMOS transistor, let us show the linear region in red color, so followed by we'll show the saturation region in green color. For VGS equals minus 0.4, we should identify where exactly the saturation region commences. So we already taken threshold as minus 0.3, so minus 0.4 minus of minus 0.3 becomes the minus 0.1. So somewhere here we have a minus 0.1. Till that there will be a linear region. This is a linear region. When VGS equals minus 0.6, okay, let me write it here so that you understand. This is minus 0.1 is the linear region commences, and here we have minus 0.3 because of VGS equals minus 0.6, minus 0.3. Till that there will be a linear region, and here we have minus 0.5 because of VGS equals minus 0.8. You subtract 0.3 from this, minus 0.3 from this, so you get minus 0.5. So we have a linear region here till minus 0.5 volts. You can see roughly how. And next, lastly, we have minus 0.7. Till that we have a linear region. Okay, we have a linear region, and here onwards there is a saturation region commences. So this is minus 0.7 volts. Okay, so that is the boundary of linear region. This side we have linear region, and the other side we have saturation region. We have a saturation region, and here we have a linear region. Let me show the saturation region in green color, the curves that represent saturation region. It commences from 0.7 and it goes like this. So we have again here, okay, so minus 0.5 it commences, here it commences at minus 0.3. This is saturation region. You can see the saturation region here. And at the bottom we have, when the VGS is more than VT, we have a cutoff region here. Okay, so we have a cutoff region on the x-axis exactly. Okay, so we have a cutoff region. So we have a linear region. This complete boundary is for linear region, and this complete boundary is for saturation region. So this line here is the mathematical boundary between the linear region and the saturation region here. So this is how one can plot the characteristics of PMOS transistor, assuming threshold voltage as minus 0.3. Next, we'll draw the characteristics of CMOS inverter. To draw the characteristics of CMOS inverter, there are three methods are there. We will go by graphical method to draw the CMOS inverter characteristics. In order to draw the CMOS inverter characteristics by graphical method, we need to understand this NMOS drain to source characteristics and the PMOS drain to source characteristics. We'll try to superimpose the PMOS characteristics on the NMOS characteristics and try to find the intersection points in order to obtain the CMOS inverter characteristics. That will be the next video we are going to present it. With that, we have come to an end of IV characteristics of MOSFET, specifically transistors. In the next video, we'll demonstrate the IV characteristics of, not IV characteristics, it's a Vout versus Vin characteristics of CMOS inverter. Thank you all for watching.